Hey everyone, so today we're going to look at inverse trig functions. If you remember inverse trig functions, we basically what inverse functions rather is what they do is they undo the effect of the function. So as in, if you remember this, let's say I had y equals e to the x, its inverse function would be ln x, right? So I had y equals, these two functions are inverse functions. And if we went ahead and graph them, right, this would be a function for e to the x. And then I would go ahead and reflect this over the line y equal to x, and I would get the function ln x, right? So it's essentially, and what does ln do? Ln undoes the effect of the exponential, right? So here we're raising that x to the exponent. What this does is it brings it back in the base, right? So we're undoing the effect. It's sort of opposite behavior. So we're interested in doing something of that sort with trigonometric functions, all right? Now, notice one more thing is that for me to have inverse functions, only one-to-one functions have inverses, all right? And so if you look at your, first of all, what are one-to-one functions? Well, one-to-one functions are, if you remember, that no horizontal line intersects the function or the graph in more than one point, right? So in a sense, one-to-one functions pass your horizontal line test. Take a look here at e to the x. No matter what horizontal line I draw, it's going to cut e to the x in exactly 1 point, right? Same with ln x. Now, if I drew a function, say x squared here, then that would not be a one-to-one function, right? That would be because the horizontal line would cut that function into 2 different points. So that sort of poses a problem for us, because if you look at your trigonometric functions, so let's for example look at sine x. So in this case, sine x, right, it's a waveform and this sort of continues forever. So obviously if I draw a horizontal line, just take a look at the x-axis, that cuts your function in a lot more than 1 point, right? And so how do we find the inverse of such functions? So what we do in this case is we do something called restricting the domain, all right? And so how do we restrict the domain? Okay, so how do we make our sine function one-to-one, right? So what we do here is we do something called restricting the domain. So if you look at your sine function, all right, so let's say this is from negative pi over 2 to say pi over 2. Okay, and then I have negative pi and pi. And then I have 1, negative 1. So now, if you graph your function, this function comes out to be this way. Right? And that's sort of one cycle of my sine function, right? And obviously, as we notice, that it is not one-to-one. Now, think about all the values that sine can assume, right? So think about the range of the sine function. And we know the range of the sine function is negative 1 to 1. Now here, if I look at this interval, right, from pi over 2 to negative, if I just look at that part of the graph, okay, sine assumes all of the values between 1 and negative 1. So it covers the entire range, okay? And so I'm going to cut off my sine function here, and then I'm going to find the inverse, right? So if I cut off my sine function here, this is what I get. Okay, so I get so that's basically how my function looks. Now, if you remember, what was your inverse function? Well, your inverse function was sort of a reflection about the line y equal to x. So I'm going to now take this graph, and now I'm going to go ahead and reflect it over the line y equal to x. Okay, so, and if you remember again, the range and the domain switch. So I'm going to have 1, negative 1. Okay, and then I'm going to have pi over 2, and I'm going to have negative pi over 2. So if this graph reflects, I'm going to get something of this sort. Okay, and so that pink line there, or that pink curve there, is one that's going to be the inverse graph of sine of x. So we're going to take a look at this in Desmos, but before that, let's go ahead and write down a couple things, right? So first of all, the inverse of the sine function is called arc sine of x, or sine inverse of x, right? So we write sine to the -1 basically. Now do not confuse that with cosecant. This is not, right? This is not equal to 1 over sine x or cosecant x. That's a big mistake that people make. Do not make that mistake. This is very different than what cosecant x is. Okay, so then what have I done here? So the first thing I've done is we restrict our domain to -pi/2 to pi/2, right? So we're just taking this much of the domain. Okay, so let's define sine inverse of x, right? So what is sine inverse of x? So what is arc sine of x? So we say that y equals sine inverse of x, okay, where -1 less or equal to x less or equal to 1, right? Because remember, again, your x values lie between 1 and -1, and y lies between -pi/2 and pi/2. Okay, so we say that y equals sine inverse of x if and only if sine of y equals x. Okay, as an example, sine inverse of 1, okay, is equal to pi/2, right? Because sine of pi/2 equals 1, and -pi/2 less or equal to pi/2 less or equal to pi/2, right? Since pi/2 falls in that interval from -pi/2 to pi/2, we can say that sine of pi/2 is equal to 1. So here's a graph of y equals sine of x, right? So we see this waveform here, okay? And like I said, what we're going to do is we're going to go ahead and restrict the domain. So I'm going to go ahead and restrict the domain from -pi/2 to pi/2, okay? So this point here, okay, this point here is going to be -pi/2, and this point here is going to be pi/2, okay? So now if I go ahead and find the inverse, as we saw here, the inverse is going to be this function here, all right, this red line here. So I'm just going to go ahead and hide this for a second. This is the inverse of my sine function, or arc sine. All right, and again, as we know for inverse functions, the domain and the range switch. So I have -1 comma -pi/2 here, which is a reflection of this about the line y equals x, and then this is your point 1 comma pi/2. Okay, so let's take an example here. We want to find the exact values of y, and so first one is sine inverse of √3/2 equals y, and the second one we have here is sine inverse of 2 equal to y. All right, so according to our definition, what is sine inverse? If you remember, sine inverse of √3/2 equals y if and only if sine of y equals √3/2 and -pi/2 was less or equal to y was less or equal to pi/2. Right, so what I'm looking for is I'm looking for an angle in radians in this case, but I'm looking for an angle such that sine of that angle gives me √3/2. Now if you remember your unit circle, or if you remember the chart that we made, we know that sine of pi/3 is √3/2. okay? The only thing we need to confirm is this angle within the interval negative pi over 2 and pi over 2? Well, it is. We know that, and we can check that if we want, is negative pi over 2 is less or equal to pi over 3 is less or equal to pi over 2, right? And thus, in this case, sine inverse root 3 over 2 is going to be equal to y, which is pi over 3. So in this case, y is going to be equal to pi over 3. Okay. Now let's take a look at the second one. So again, if sine inverse of 2 equal to y, what this means is we have sine of y equals 2, right, where negative pi over 2 less or equal to y less or equal to pi over 2. But the question is that possible? If we remember, my sine function, the maximum value it could take was 1, and the minimum value it could take was negative 1. So all the values have to be between 1 and negative 1. Well, 2 certainly is not between 1 and negative 1, right? And so there is no y such that sine of y equals 2, right? So thus in this case, that you cannot solve that, and so there is no y, right? So sine inverse of 2 is undefined.